Hello everyone. In the today's class we will start with the AC analysis. So the BJT transistor, what we are using it for AC analysis. That means basically this BJT transistor is used for an amplification purpose. That is the main application of using this BJT transistor. So now before we use that, we are going to understand that you need to model this transistor to work like an amplifier, right? So model means a model is a combination of a circuit elements like resistance, current source, dependent current source, independent current source, likewise. Okay, so now a model is a combination of these circuit elements. You're going to choose that best approximates the actual behavior of a semiconductor device under specific operating conditions, right? Since you are using this as an amplifier, you need to ensure that the transistor should be working in specific operating condition, right? So that we have discussed in the DC analysis part in my previous videos. So you know that how to get a specific operating condition. So now we are going to model that so that the transistor in a particular configuration should represent that operating condition. Okay, so there are different ways of modeling this BJT transistor, like a resistance model, pi model, H parameter model, and so on. So in the today's lecture we will be discussing about the resistance model, RE model for a transistor. Okay, so this BJT transistor which is having the three terminals can be configured into different ways. In that particularly we will discuss about common emitter configuration. Okay, we are going to discuss about common emitter configuration. So this is collector, emitter and base of the transistor. We are making this emitter to be common for both input and output. So you are giving input to the base terminal with respect to reference, and you are taking the output at the collector terminal with respect to reference. That means the emitter becomes reference or the common for both input and output. Hence this is common emitter configuration. Okay, so now here to operate this, we know that this BJT is made up of three layers, that is NPN transistor it is about. In this, one is emitter terminal and one is collector terminal, and the P junction will be of base terminal. Okay, so this becomes an NPN transistor when you connect this collector terminal to the higher potential. You connect the collector to the higher potential and emitter will be connected to the lower potential. Okay, for an NPN transistor, and this is the symbol of a transistor which represents this arrow going outside the transistor, representing outside the transistor. That means it represents that the majority charge carriers are electrons and the current flowing in this transistor is due to electron. Okay, so now you have two junctions and three layers, NPN layers, and P is connected to the base and N is connected to the emitter and collector. So here to operate this, you need to ensure that the base to emitter junction should be forward bias and base to collector junction should be reverse bias. Okay, so only when you ensure that base to emitter junction is forward bias, then you make this device on and to operate it accordingly, right? So now we are going to use this for an amplification purpose. So you need to make this base emitter junction to be forward bias. So now to represent that, we are going to model this into equivalent diode model first. Okay, so this is an diode model. So here the transistor in a common emitter configuration is operated by giving an input voltage to the base. Okay, so that the input current IB is obtained and that is controlling the output current IC. Okay, that means this is basically a current controlled current source. So to represent this in a diode model, we have, so this is my base, this is my collector and this is my emitter. Okay, the emitter is connected to ground, it becomes common for both input and output. So my input is given to the base terminal with respect to reference, okay, and output is taken from collector to emitter. This is my output V0 from here to here. So output is basically a current IC which is drawing from the collector terminal, which is connected to the higher potential VCC. Okay, so here it is VCC. By making this base to emitter junction diode, sorry, this has to be represented as diode. This diode has to be forward bias. You have to make this base emitter junction forward bias in order to get the current IC from collector to emitter. Okay, so now this is the diode model first. Okay, then we replace this diode with equivalent resistance to represent the resistance model. Okay, so now this is the input current IB which decides your output current IC. Okay, so this is your diode model. So now we are going to represent this two equivalent resistance model by replacing this diode into its equivalent resistance. So this is current source, constant current source, and this is resistor, and this is base terminal, collector, emitter, and this is RE, which is the equivalent resistance of the diode in forward bias. Okay, so now here this is my input given to the base terminal with respect to reference, and this is my output IC. Okay, and the current flowing through the RE is IE. Okay, and these three currents, which are IE, IC, and IB, are related by your IE is equal to IC plus IB. This is your total current IE. Okay, and IB is your input current and IC is our output current. So input current and output current is related by IC is equal to beta times of IB. Okay, so beta is nothing but current amplification factor here, in which it amplifies by beta times. The output current is amplified by beta times. So your IE will be IC is beta times IB plus this IB as it is. So your IE is beta plus 1 times of IB. Okay, so here this is your IE expression. Since beta is very large compared to 1, so your IE can be approximated to beta times of IB. That means your IC is almost equal to IE. Okay, so this is the current relations what you have in this configuration, the common emitter configuration. The input is IB, output is IC, and the current flowing through the resistance finally it is IE, right? So this is the RE model. Now to do the AC analysis, we have to represent this in a two-port network. So two-port network means basically it consists of two ports, input port and the output port. So we are going to represent this in a two-port network. That we will represent it like this. So this is my two-port network. This is my input port, port 1. This is my output port, port 2. Okay, so port 1 is my input port, port 2 is my output port, right? And this is my equivalent resistance RE what we have here, and this is my input current IB, and this is my output current which is IC, which is equal to beta times of IB. This is my output current. Okay, so now here to find out the input impedance Zin, which is the impedance seen with respect to input terminal Vin, which is given from base to reference. So the terminals of these are basically the base terminal, collector terminal, and the emitter terminal. So the emitter is connected to ground here. So hence my input voltage is from base to reference, which is emitter. Okay, this is my input impedance, which is seen between V in and I in. So Z in is nothing but V in by I in. So this is my I in. Okay, so here I in is nothing but my IB, and V in is nothing but base to emitter VBE. Okay, so V in by I in, I can write it as VBE by IB. Okay, this is my Z in. So VBE is nothing but the voltage across this resistance RE model. VBE is nothing but the voltage across this resistance RE, which I write it as RE, and the current flowing through the resistance RE is IE. Okay, so that is my current flowing through the resistance IE. So but IE is 1 plus beta times of IB. So this is my base current IB. Okay, so now my VBE will be 1 plus beta times of IB into RE. Okay, so I will continue the same in the next sheet. So my Z in, which is equal to V in by I in, whereas V in is VBE and I in is IB. VBE is nothing but the current through the VBE is nothing but the voltage across the resistance RE, which is equal to RE into IE. RE into IE. So IE in terms of IB, 1 plus beta times of IB. Okay, so I will represent the same in a two-port network, that is, so this is my IB, this is my IC, which is equal to beta times of IB. This is my V in, what I am giving from base to reference. This is my collector terminal, right? So this is my Z in, what I am calculating now. Okay, which is V in by I in. So here 1 plus beta, as I told, beta is very large compared to 1. I can approximate this 1 plus beta as beta. So this is RE into beta times of IB is your VBE. So now substituting this in this equation, Z in, which is equal to VBE by IB, I can write it as RE into beta times into IB divided by IB. So IB I will cancel, and this will be equal to beta times of RE. So this resistance will be beta times of RE. Okay, so this is the resistance or the input impedance, which is seen with respect to input current, which is nothing but IB. Okay, so now this is my input impedance, and the output impedance we can also represent this by knowing the output characteristics of the BJT, which we plot it across VCE, which is my output voltage, and IC is my output current. So now for a constant value of input voltage or an input current IB, I will plot this VCE, which will be initially varying proportional to VCE, and then it will be constant. So this is for a constant IB. So this is my output characteristics for variation of VCE and IC. Initially it will be linear and then it remains constant. So here this portion is called as saturation region of operation for the BJT, and this is the active region of operation for the BJT. Okay, so now here it is almost equal to constant, the current will remain constant. That is what we are representing here, that is constant current source which is dependent on IB. If IB increases, again you will get a different curve. If it decreases, again this curve will decrease like this for a different value of IB. Okay, so now here the slope of this, if I take a slope of this, slope means change in Y, which is change in IC divided by change in VCE. Output current by output voltage is nothing but output conductance. If it is a straight line, the output conductance will be a 0. If I take the inverse of this output conductance, I will get output resistance, and the inverse of this 0 will be infinite. 1 upon 0 is infinite. Okay, so that is what I am representing here as an output resistance R0. So the slope, if it is ideal, it will be straight line. So the slope is G0 will be equal to 0, and the inverse of slope, which is R0, 1 upon G0, will be 1 upon 0, which will be infinite. That will be large, which we are representing it the output resistance of the current source, constant current source. So this is the small signal model represented in a 2-port network for common base configuration. Okay, so if I take it for the common emitter configuration, so now if I take it for the common base configuration, that means base is common or reference with respect to input and output. Okay, so now I will take an NPN transistor again, so that the arrow is showing outside. So emitter is connected to the input terminal, and collector is taken at, means output is taken at the collector terminal. This is my IC, and this is my base which is connected to the ground. So now if I represent this in a small signal model, so I will represent it like 2-port network like this. Okay, so this is my V in, this is basically emitter terminal, this is base, and this is collector. So my input current is IE, but the output current will be IC. So IC will be alpha times of IE. So alpha is nothing but beta upon 1 plus beta. As beta is very large compared to 1, alpha will be almost equal to 1. Theoretically it will be equal to 1, or practically it will be slightly less than 1. Okay, so now to find out the input impedance of this Zin is V in by I in. So I in here is IE itself. Okay, so this V in will be the voltage across these two terminal. V in is RE into IE. This will be IE cancels, and this will be equal to RE itself. So Zin is equal to RE. Okay, so you see here the input impedance Zin will be equal to RE with respect to input voltage and input current in case of common base, whereas here in the common emitter the input impedance is beta RE, because the input current I in is nothing but IB it is. Okay, IB, and the current flowing in the resistance RE, in the resistance RE model, it is basically in current IE. Okay, so the input current is IB, whereas the current flowing through the resistance RE is IE. Hence, when you are representing it in a small signal model, the input current I in will be IB for the common base configuration. So hence, with respect to the input current IB, the input impedance is beta RE. Whereas in the case of common base, the input impedance with respect to input current is IE. So with respect to IE, the input impedance is RE. Right? So this is the small signal model or the resistance model in a two-port network. So and also we can represent the R0 here, so which is obtained by output characteristics of the common base configuration, whereas in this the output voltage is VCB and the output is IC, output current is IC, and for the constant IE you will get the curve which is like this, IE constant, the curve is like this, and this you are again operating in a constant current region. That means you are representing it in a constant current source by taking the slope of this change in IC divided by change in VCB, which is output conductance. If it is a straight line, it will be small, ideally 0. If I take the inverse of G0, which is R0, which will be equal to infinite. So that is what we are representing this with the output resistance R0 for this common base configuration. Okay, so this is the resistance RE model for the common emitter and common base configuration of an BJT amplifier circuit. Thank you.